Welcome to CECS 228. Today we're going to continue our lecture notes on Relations Part 1, which deals with some of the basic definitions and operations on relations. In the last lecture video, we didn't actually get to cover the operations, so that's where we're going to pick up today. Okay, so in the last lecture, we took a look at some relational databases and some operations that we can carry out on those databases. So namely the selection, projection, and join operators. We're now going to generalize that and take a look at what operations we can apply to any relation. And this is actually going to feel very familiar because all of the operations that we're going to discuss, we've seen when we've talked about sets. Okay, starting with the union. So in example 7, they give us two relations, R1 and R2. They both take elements from the set A of 1, 2, 3 to the set of elements 1, 2, 3, 4. And R1 contains 3 elements. The ordered pairs 1, 1, 2, 2, 3, 3. R2 contains 1, 1, 1, 2, 1, 3, and 1, 4. And part A is asking us to find the union. So if you recall, the union in sets is the set of all elements that are present in either the first or the second set. So what I'm doing here is I'm taking all of the elements from R1, the 1, 1, 1, 2, 1, 3, from R2 and 1, 4, and then we add to that same set the elements from R1, so that'd be 2, 2, and 3, 3. And notice, even though we did list, or they do give the order as R1 union R2, I started listing the elements of R2 first, and it doesn't affect the result. In a set, the order doesn't matter, so we can start by listing elements of R2 first, or R1, or maybe have them mixed up, and it's not going to affect the correctness of our answer. Okay, for part B, they're asking us to find the intersection of R1 and R2. An intersection means all those elements that are shared in common between the two sets. So if we go back to R1 and R2 to see which elements they have in common, R2 only has ordered pairs with a first coordinate of 1. That means that in R1, the only pair that is shared in common is the 1, 1 and nothing else. So that means that the intersection contains only one element, and that is 1, 1. For part C, they're asking us for the difference between R1 and R2. And so what that means is that we're looking for all elements that are part of R1 but not R2. And I guess it's a good idea to maybe draw a diagram, a Venn diagram, to help us illustrate that situation. So we're looking for all of the elements that are part of the first set but not part of the second. So that means that we could potentially have some that intersect, such as the 1, 1, that would be left out of this difference. So if we go back to R1, R1 contains the element 1, 1, but that's part of R2, so we don't include it. And then there is 2, 2, and 3, 3, which are both not part of R2. So that means that the difference R1 minus R2 would be elements 2, 2, and 3, 3. And then we switch the order of the difference. In this case, we're taking a look for R2 minus R1. So this is R1 and this is R2. In the diagram, we're looking for all elements that are part of only R2. If we go back, R2 contains 1, 1, same as R1, so we wouldn't include that as part of the difference. Then we would have 1, 2, 1, 3, 1, 4, all of which are not part of R1. So the only ones that are in the difference R2 minus R1 is the 1, 2, 1, 3, and 1, 4. And so it works exactly the same way as for sets, except that now instead of having elements that are a single value or maybe a single letter, we have ordered pairs or potentially n-tuples. Okay, example 8 is telling us that A is the set of all students and B is the set of all courses at a school. Suppose that R1 consists of all ordered pairs A, B, where A is a student who has taken course B, and R2 consists of all ordered pairs A, B, where A is a student who requires course B to graduate. What are the relations R1 union R2? Okay, so again, the union means that the element is found in either the first set, R1, or potentially the second set, or maybe in both. So and that would mean that it's going to consist of all ordered pairs who, where A is the student who has satisfied at least one, meaning they either have taken course B, and that means that they would be part of R1, or they have to take course B in order to graduate, so that means that they are a part of R2, or both. Okay, so we're going to write that. So where A is a student who has either taken course B or must take course B to graduate, or both. Okay. Now part B is the intersection, so that means that it consists of all ordered pairs A comma B, where A is a student that satisfies that they are both found in R1, so that they have taken course B, and they have to take course B in order to graduate. All right, now part C is exclusive OR. So we're looking at R1 exclusive OR R2. That means it consists of all of the ordered pairs A comma B, where A is a student who has taken course B or has to take course B in order to graduate, but not both. The difference, R1 minus R2, would be the set of all ordered pairs where A is a student who has taken course B but does not need it to graduate. Because remember, R1 is all ordered pairs where A is a student who has taken course B. So if we take away from that all students who need course B in order to graduate, it would result in all students who have taken course B but don't need it to graduate. Okay. Now, if we reverse the order, R2 was all of the students who need course B in order to graduate. And if we take away from that set all students who have taken course B, we're going to be left with all the students who need to take course B to graduate but have not taken it. All right, and now we take a look at something that is analogous of composition of two functions. So this is called the composite of two relations R and S. So the composite of two relations R and S is denoted S of R, and it's the relation consisting of ordered pairs A comma C, such that A is part of the set A, C is part of the set C, and there exists some element B in set B, such that A comma B is an R and B comma C is an S. Okay, so if you recall from functions, whenever we saw f of g, that meant that g was passed in as an argument into f. So that meant that the output of g of x had to be part of the domain of f of x. Similarly, when we have the composite of two relations, such as S of R, we need to make sure that if R maps from A to B, that S begins taking inputs from the set B out into some other set C. Okay, so basically, the output set of R has to be the input set of S. Otherwise, the composite won't be well defined. Okay, so let's take a look at a numeric example to make better sense of this. Example 9 reads, what is the composite of the relations R and S, where R is a relation from 1 to 3 to 1 to 3, 4, and R is defined by elements 1, 1, 1, 4, 2, 3, 3, 1, and 3, 4, and S is a relation from 1, 2, 3, 4 to 0, 1, 2, with S being defined by elements 1, 0, 2, 0, 3, 1, 3, 2, and 4, 1. Okay, So the first thing that I'm going to do here is I'm actually going to make sure that the output the set of outputs pertaining to R is the same as the set of inputs for relation S. And so R takes from the input 1, 2, or 3 to the output 1, 2, 3, 4. And then S takes from input 1, 2, 3, 4 to output 0, 1, 2. And so that's good because that means that the output of R agrees with the input of S. That means that we're going to be able to find these mappings from R to S. So let's go ahead and list these out. R takes input elements 1, 2, 3 to output elements 1, 2, 3, 4. Then S is going to take those to 0, 1, 2. 1 is part of R, so that means that we have this mapping. 1 gets mapped to 4 as well. Then 2 gets mapped to 3. 3 gets mapped to 1. 3 gets mapped to 4. Okay, now we take a look at S. S maps 1 to 0, 2 to 0, 3 to 1, 3 to 2, and 4 to 1. Okay, so now based on that, we can start looking for the composite. 1 gets mapped to 1 to in R, but then 1 gets mapped to 0 in S. So S of R is going to include the element 1, 0. Okay. Then since 1 here doesn't map to anything else, we can now take a look at 1 mapping to 4 and then 4 mapping to 1. So that means that we're going to have an output element of 1, 1. All right, now at that point, we've taken care of all possible outputs of 4, and that means that we're done considering input of 1 under relation R. We next move on to input of 2. So 2 gets mapped to a 3. Let me just draw this a little bit more solid. So 2 gets mapped to 3, and then 3 gets mapped to 1. So that means that we're going to have an element 2, 1. And then 3 also gets mapped to 2, so that means that we'll have an element 2, 2. Okay. Now at that point, 3 doesn't have any more outputs, and 2 doesn't have any more outputs, so we're done considering the input 3 under relation R. Okay, the next one is input of 3. 3 gets mapped to 1, and 1 gets mapped to 0, so we're going to have an element 3, 0. Then 1 doesn't have any more outputs under S, so that means we're done at that point with the 1. We can move on to the next output of 3 under R, and that would be 4. So 3 gets mapped to 4, and 4 gets mapped to 1. So that means that we have an element 3, 1. And then since 3 doesn't have any more outputs and 4 doesn't have any more outputs, that means that we are officially done with the input of 3. And so those would be all possible ordered pairs that will be part of the composite of S with R. Related to the definition of composite is the definition of powers of R. So we're going to let R be a relation over the set A. So that means that A is both the set of input elements and the set of output elements. The powers of R to the n, for n being 1, 2, or anything greater, are defined recursively in the following manner. So R to the 1 is simply R, but then R to the n plus 1 is defined to be as R to the n a composite with R, or composed with R. Okay, so what that means is that we take a look at the outputs of R and take them in as inputs of R to the n. And so we're actually going to exemplify that with the next set. R is the relation with elements 1, 1, 2, 1, 3, 2, and 4, 3. And they're asking us to find the powers of R to the n for n being 2, 3, 4, and anything greater. So we're going to start by finding R to the second, which means this is R composed with R. And so we're going to draw similar to what we did in the previous problem, the set of inputs, and the set of inputs are 1, 2, 3, 4, to the set of outputs, which are also 1, 2, 3, except for the 4, so I guess just 1, 2, 3, but technically we include the 4 there because if you recall, the powers of n are defined over relations that take the same set as inputs to outputs. So 1 gets mapped to 1, and then 2 gets mapped to 1, and then 3 gets mapped to 2, and then 4 gets mapped to 3. Okay. And then R is going to repeat that the same mapping. So 1, 2, 3, 4. 1 gets mapped to 1, 2 gets mapped to 1, 3 gets mapped to 2, and 4 gets mapped to 3. So now that we have this diagram, we can read what R of R is going to contain. 1 gets mapped to 1, and then 1 gets mapped to 1, so that's simply going to be 1, 1. And since 1 here doesn't have any more outputs, same as the output 1 from the first mapping doesn't have any more outputs, that means we're done with this element. We can continue on to 2. 2 gets mapped to 1, and 1 gets mapped to 1, so we'll have the element 2, 1. And then no more outputs for 1, no more outputs for 2, so that means that 2 is done. Next we consider 3, so 3 gets mapped to 2, and 2 gets mapped to 1, so we'll end up with an element 3, 1. Then 2 doesn't have any more outputs, and 3 doesn't map to anything else, so we're done with the 3. And last we consider the 4. So 4 gets mapped to 3, 3 gets mapped to 2, so we'll end up with a 4, 2. And then 3 doesn't have any more outputs, 4 doesn't have any more outputs, so that is that. So that means that R to the power of 2 will contain these 4 elements. So now we have R3 that we need to find, and it is defined recursively, so it's going to be R2 of R. And what that means is that I'm going to now take this R2 and take a look at that mapping. So first we have to take R2 itself and then R squared. We'll draw that mapping. So starting off with R, we'll have 1, 2, 3, 4 mapping to 1, 2, 3, 4. And R2 also has to map to 1, 2, 3, 4. R maps 1 to 1, 2 to 1, 3 to 2, 4 to 3. And then R2 maps 1 to 1, 2 to 1, 3 to 1, and 4 to 2. Okay, so now we'll start with 1 maps to 1 and 1 maps to 1. So that'll be the element 1, 1. Then 1 doesn't have any more outputs either here or here, so we're done with that element. We'll move on to 2. 2 maps to 1 and 1 maps to 1, so we'll end up with 2, 1. Then next we'll move on to 3. 3 maps to 2, 2 maps to 1, so we'll have an element 3, 1. And 3 doesn't have any more outputs, and 2 doesn't have any more outputs, so we're done with 3. Then 4 maps to 3, and 3 maps to 1, so we'll end up with the element 4, 1. And then 3 doesn't have any more outputs, and 4 doesn't have any more outputs, so we're done with that one. And that is R3. Next, we're going to consider R4. R4 is now going to be R3 of R. So again, we'll draw what R maps. And we'll draw what R3 maps. So 1 to 1, 2 to 1, 3 to 2, 4 to 3. Then R cubed is 1 to 1, 2 to 1, 3 to 1, 4 to 1. Okay, we'll have an element 1 to 1 to 1, so that's 1 comma 1. Then 2 to 1 to 1, so that's 2 comma 1. Then 3 to 2 to 1, so that's 3 comma 1. And 4 to 3 to 1, so that's again 4 comma 1. Now notice, they did write dot dot dot, which means they want us to find higher powers, but if you notice, all of these are going to repeat, right? If I try to find what R5 is, that's going to be R4 of R. And when we draw the diagram, since R4 turned out to be exactly the same thing as R3, we're going to have the same diagram, but with R4 here listed instead. So when we try to find the elements, we're going to end up with the same elements. So that means that R to the n will be 1 comma 1, 2 comma 1, 3 comma 1, and 4 comma 1, for n being greater than or equal to 3. The only one that's different is R squared, that contains a 4 comma 2 instead of a 4 comma 1. We're now going to move on to relations part 2, which deals with representations of a relation, starting with matrices. So if you've never seen a matrix before, a matrix is just a collection of elements that consist of rows and columns. So in general, we like to say that we have m rows and n columns, and the matrix will look something like this, where each subscript, like for example 1 comma 1, this corresponds to row 1, column 1, row 1, column 2, all the way down to row 1, column n. On the next row, we would have element 2, 1, which means it's on row 2, column 1, or element 2, 2, which means it's on row 2, column 2, so on and so forth. The very last row would be the mth row, so we would have an element em1 for the mth row first column, and then nth row second column we would find the element em2 all the way down to the element emn. So we're going to be using matrices to represent a relation R, and the way that we're going to be doing it is by letting the matrix consist of elements mij, so that means on the ith row, jth column, we'll have a number 1 if the ordered pair ai comma bj is part of the relation. So what that means is that if from the set of inputs the ith element paired with the jth element of the set of outputs is part of the relation, then the ijth element in the matrix will be a 1. Otherwise, it's going to be a 0. Okay. So let's try to exemplify that definition with this example here. So suppose that R is a relation from the set of inputs A, B, C, D to the set of outputs 10, 20, and 30. Identify the elements of the relation R if it's being represented by this matrix. Okay. So remember, i's are represented, meaning the rows, the ith row is being represented by the inputs. Okay, so the rows here represent inputs A, B, C, and D. And then j's correspond to the columns. Okay, and those are the outputs. So this represents output 20, output 10, output 20, and output 30. So A in this case is not mapped to 10 because we have a 0 at the first row, first column, which would represent the ordered pair A, comma 0. There is a 1 in the first row, second column, so that means that A does get mapped to 20. So that means that R contains the ordered pair A, comma 20. There is also a 1 in the first row, third column, so we would have A, comma 30. Yeah. Then if we move to the next row, which represents the input B, we see that there is a 0 at output 10, at 1 at output 20, so there is an ordered pair that is B, comma 20, and then a 0 at 30, so there is no B, comma 30 as part of the relation. We have a C, comma 10, but no C, comma 20 or C, comma 30, and then for D, there is a D, comma 30. And that is in general how we use matrices to represent relations. We'll use the rows to represent input and the columns to represent output. If you have a 1 at the ijth position, that means that the ith element of the input gets mapped to the jth element of the outputs. So why would we want to use matrices to represent a relation? Well, it turns out that looking at some of the properties of a relation are a lot easier to pick out in a matrix than from the ordered pairs. Specifically, it's very easy to see whether a relation is reflexive or not if we see the matrix of that relation. Okay, so recall that a relation on A is reflexive if for every element in the domain, A, comma A is part of that relation. So in terms of matrices, if you think about it, that means that if this is A and this is A, and remember it's a relation on A, so the inputs and the outputs are going to be the same. Okay, so the first row is representing the same element as the first column. Okay. So if A, comma A is part of the relation, that means that we'll see a 1 at this position. We'll also see it on the second row, second column, on the third row, third column. So we're just going to see 1s across the diagonal, which means that we don't even need to go and look for every single ordered pair if we have the matrix. If we have the matrix and see just 1s, then automatically that means that it's reflexive. Let's think about symmetric. What was by definition a symmetric relation? A symmetric relation meant that for every element, every ordered pair A, comma B that's part of the relation, B, comma A also has to be part of the relation. So if we think in terms of matrices, how is that going to look like? Let's take a small relation just to consider it. Like if we have, let's say, a relation that maps 1 to 2, that means that 2, comma 1 also has to be part of the relation. And maybe we have the element 0, comma 0. So this would be a relation from the set of elements 0, 1, 2 to 0, 1, 2. And then if we draw the matrix representation for it, we would need 3 rows and 3 columns, 1 to represent the 0, 1 to represent the 1, and 1 to represent the 2. And we would have, for 0, a 1 at the first row, first column, then 0s everywhere else because 0 doesn't get mapped to any other element. For the 1, it gets mapped to 2, so that means that we would have 0, 0, 1 on the matrix. And then for 2, 2 gets mapped to 1, so we would have a 0, 1, 0 on the matrix. Okay, so what do we notice? Well, we said whenever there is the element A, comma B, there has to be the element B, comma A. So if I have a, for instance, a 1, comma 2 here, there also needs to be a 2, comma 1. So we use the diagonal kind of as a mirror, and all of the 1s have to reflect across that mirror. Or another way to think about it is if I were to switch the rows and columns, meaning if I were to make this row a column instead, I would get exactly the same matrix back because all of the elements reflect across this diagonal. Okay, so in general, all ones and zeros. Reflect across the diagonal. And I'll say the main diagonal here. Okay, so the one that begins at 1, 1. Okay, so i.e., if we make rows columns, and vice versa, we get the same matrix. And just to illustrate it again, if you're not too convinced about this part, that if we make rows into columns and columns into rows, that we get the same matrix, let's try it here. I'll take this first row, which is a 1, 0, 0, and make it a column. So we would get a 1, 0, 0. Then I'll take the second row, which is 0, 0, 1, and I'll make it into a column, so that would be 0, 0, 1. And then this last row, which is a 0, 1, 0, and make it into a column. And then notice we get exactly the same matrix back. 1, 0, 0, 0, 0, 1, 0, 1, 0. So these two are equal, which means that the relation is symmetric. And again, the reason why is because we simply see that these elements reflect about the diagonal. Okay, what about antisymmetric? Well, what does antisymmetric even mean? Antisymmetric means that for every element A comma B that is part of the relation, then B comma A will be part of R if and only if A is equal to B. Okay, so meaning the only time when this can happen is when both of the coordinates are the same. So if you have like a 1, 1 or 2, 2, that's okay. But anything aside from that, like if I have a 1, 2, then a 2, 1 cannot be part of the relation. And so I'll just write here an example of a relation that is antisymmetric. So we can have 1, 2, we can have 0, 0, and maybe we can have 1, 1, but we definitely cannot have a 2, 1. Okay, so I'll just include a 2, 2, just to have an extra 1 on that matrix. So if we draw the representation for it, again, remember we have, and I'll use one less row, one less line so that we have some space to write other information. So we have input 0, 1, 2, 0, 1, 2. 0 gets mapped to itself, so we have a 1 at row 1, column 1, and then nothing else. 1 gets mapped to 2, and it gets mapped to 1, so we'll have a 1 here, and a 1 here, and a 0 everywhere else. And then 2 gets mapped to itself, and that's about it. Okay, so for the matrix, when you have an antisymmetric relation, it means that it's okay to have 1s along the diagonal, but then if you have a 1 at the ijth position, you can't have a 1 at the ji's position. Okay, so if we use a diagonal, kind of like what we did earlier as a mirror, now you should see the opposite symbol for a 1. Okay, if this is a 1, this cannot be a 1. All right. Let me just write that in general. So in general, 1s are allowed along the diagonal. But if position ij contains a 1, then position ji cannot contain a 1. So that means it must contain a 0. so we're now going to apply those properties that we saw of a matrix representing a relation onto example number 2. In example number 2, it reads, suppose that the relation R in a set is represented by the matrix MR. Is R reflexive, symmetric, and or antisymmetric? And one thing they don't mention here is what are the domain and codomain of the relation. We're going to take it that it's going to be from a set A to a set A, since we have the same number of rows and the same number of columns. And so I'll just include here from set A to set A. Alright, so is R reflexive? In order for R to be reflexive, recall that on the matrix, if it has all ones along the main diagonal, then that means that it will be reflexive. And in this case, we do see those ones along the main diagonal, so that means that, yes, we have all ones along the main diagonal. In terms of the relation, what that means is, let's say that this is representing inputs ABC and this is outputs ABC. It means that we have the elements A, B, B, and C, C, which is the requirement of reflexivity. Okay, that's the definition of a reflexive relation. It means it contains, for every element in the set A, which we're assuming is ABC, we'll have the ordered pair A, A. So yeah, all ones along the main diagonal means that it is reflexive. What about symmetric? Okay. Well, for symmetric, we said if we use the main diagonal as a sort of mirror, that means that wherever we see a 1, if we see a 1 on the row 2, column 1, that means that we also have to see a 1 in the row 1, column 2. Okay, so if we have a 1 at the ijth position, then there should be a 1 at the jith position. Or in other words, it just reflects across the main diagonal. And so here that looks good. We'll see a 1 at row 2, column 3. So we should be seeing a 1 at row 3, column 2. But as it turns out, there is no 1 at row 3, column 2. So that means that it is not symmetric. Now, if we try to give a reasoning why, we can now look at the elements of the relation. This means that B, C is part of the relation. But the 0 means that C, B is not part of the relation. So it's not going to be symmetric. All right, finally, is it antisymmetric? Okay, antisymmetric means that wherever we have a 1 in the ijth position, then the j first position cannot have a 1. Okay, so if we take a look here, we have a 1 at the second row, first column, but we don't see a 0 at the first row, second column. So that means that this is not antisymmetric. Okay, so this is no, because B, A is part of R, and A, B is also part of R. So it's not antisymmetric. Okay, so that is how we use matrices to read some of these properties of a relation. For the next part is we're going to take a look at the union, okay, some of the operations on relations. We're going to take a look at how we can find those using the matrix representation of the relation. So we're going to, in general, let E and D be matrices with dimensions m times n. So that means that there are m rows and n columns that consist of solely ones or zeros. Then the disjunction of the two matrices is going to be defined component-wise. So that means that we take the ijth element of matrix E and then the ijth element of matrix D and take the disjunction of the two elements. Okay, so for instance, if we have the matrix that is 1, 0, 0, 1. Disjoint, obtain the disjunction with 1, 1, 0, 1. That means we would take first row, first column of the first matrix, disjunction with first row, first column of the second matrix, 1 or 1, which is going to result in a 1. Then first row, second column with first row, second column of the second matrix. So 0 or 1, that's this expression here, is going to give us a 1. Then 0 or 0 will give us 0 or 0, that's a 0. And finally 1 or 1, that's 1 or 1, so that gives us a 1. Okay, so now that we know in general what the union is, or what the disjunction of two matrices is, we're going to look at the union of two relations in terms of the matrices. So suppose that we want to find R1 union R2, then the matrix of that union is the same as the matrix of R1 disjunction with the matrix of R2, where MR1 and MR2 are matrix representations of R1 and R2 respectively. Okay, so for instance, actually before we look at an example, let's also look at the intersection since it's very similar. Intersection will be defined also component-wise. So we take the ijth element of the first matrix and then conjoin it with the ijth element of the second matrix. Okay, so as a short example, if we have 1, 0, 0, 1 conjoined with 1, 1, 0, 1, then we would take 1 and 1, so this expression which results in a 1, then a 0 and 1, which is a 0 and 1 results in a 0, then a 0 and 0, that would result in a 0, and then a 1 and 1, which results in a 1. Now, according to this definition, the intersection of the two relations can be represented by a matrix, and it's going to be given by matrix of the intersection is the same as matrix of R1 conjoined with matrix of R2, where MR1 and MR2 are the matrices of R1 and R2 respectively. Okay, so let's take a look at example 3. Here we have two relations, R1, R2 over some set A, and it's represented by these matrices. We want to find what is the union, R1 union R2, and the intersection as well. So let's start off with the union. What is M matrix of R1 union R2? That is going to be the disjunction of the two matrices. So here is the matrix that represents R1. So disjunction, the matrix that represents R2. So this is MR1, this is MR2. Right, and it's defined component-wise. So if I take a look at the first row, first column, that means I need to look at the first row, first column of the second matrix as well. So here we'll have a 1 or 1, that means we have a 1. Then a 0 or 0, that means we have a 0. A 1 or 1, that means we have a 1. And we have a 1 or 0, so that's a 1. A 0 or 1, that's a 1. A 0 or 1, so that's a 1. And last row, 0 or 1, that's a 1. 1 or 0, that's a 1. 0 or 0, that's a 0. Okay. Now let's translate it back to the elements of the relation. So if this is relation that takes elements ABC to ABC, R1 is going to contain the elements AA, A to C, then B to A, and C to B. Okay, so I have a total of 4 ones, which means we have a total of 4 elements for the first relation. For the second relation, again, we're assuming it's from ABC to ABC, Second relation will contain element AA, element AC, element BB, element BC, and element CA. Okay, so here we have 5 ones, which means we have 5 elements as part of relation 2. Now, if we try to take the union of the two elements, we would end up with, let me just go ahead and write them here, we would end up with AA, AC, BA, CB, that's from R1. Then from R2 we have AA, which is already listed. We have AC, which is already listed. We also have BB, which is not listed, so I'm going to write down. BC, which I'm going to write down. And CA. Okay, so I'll write CA over here. Okay, so that's a total of, let's see, 2, 4, 6, 7 elements. If we compare that with the matrix that we got representing the union, we see there are 7 ones. So that means there are 7 elements. And if we were to write out what those elements are, we have A, B, C, A, B, C. It would be AA, AC, so that's these two here. BA, that's this one. BB, that's here. BC, that's here. CA, so that is here. CB, that's here. And that's it. So those would be all the elements. And so then we see that both of these are equivalent, but it was probably a lot faster to find this matrix representation than having to compare elements every time and write down the elements. Okay, so that is for the union. Let's take a look at the intersection now. So the matrix representing the intersection of R1 and R2 will be the matrix, the conjunction of matrix 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0. That's for R1. And then conjunction with matrix for R2, which is 1, 0, 1, 0, 1, 1, 1, 0, 0. And that is going to be 1 and 1, which is 1, 0 and 0, which is 0, 1 and 1, which is 1, 1 and 0, which is 0, 0 and 1, that's 0, 0 and 1, that's 0, 0 and 1, that's 0, 1 and 0 is 0, 0 and 0 is 0. So then what this is saying, let's go in the reverse order now. Let's read off the elements from the intersection, the elements of the intersection from the matrix. So from the matrix, that means that A comma A should be part of the intersection, and A comma C should be part of the intersection, but nothing else. Again, if we refer back to the relations, we see that they share A comma A, they share A comma C, but nothing else is shared in common, right? BA is not found here, CB is not found here, and same thing for BB is not in R1, BC is not in R1, and CA is not in R1. So that's how we can use the matrix to find intersection and union. What about composition? And for composition, we can also find it using some type of matrix operation, but in order to do so, we need to know what the Boolean matrix product is. So we're going to let A be an n by p matrix. What that means is it has n rows and p columns, and B be a p by m matrix. So that means that it has p rows and m columns. And then the entries of both matrices consist of only zeros and ones. The Boolean product of the two matrices is going to be defined by this symbol. First of all, the notation is Boolean matrix product. It's going to give you some element Cij, where Cij consists of the conjunction of the element at the ith row first column in A with the first row jth column in B, and then disjunction A1 2 conjunction with B2J all the way down to AIK conjunction with BKJ. So if you notice, the outer subscripts are always I and J, I and J, I and J. The only ones that change are the middle ones. So it goes 1, 2, 3 all the way down to K, where K is, well, K should be our P, actually. So let's take a look at how that works. So the subscripts can get a little obscure. So we're going to find the Boolean matrix products of the matrices. So technically this should be A and B. This is just a typo. So we can call this A, and this is B below. So A matrix product, Boolean matrix product. Let me just rewrite the matrices. We have 1, 0, 1, 1, 0, 0, 0, 1, 0, product with 1, 0, 0, 1, 1, 0. Okay. What we have to be careful here, we have to make sure, is this is a 3 rows by 3 columns. This is 3 rows by 2 columns. So we always have to make sure that the number of columns of the first matrix agrees with the number of rows of the second matrix. And the reason is this. What we do is we actually take the first row with the first column, and we take the conjunction of the entries and then the disjunction of the result. So what I mean by that is the following. In order to get the first row, first column, we take 1 conjunction with 1, or 0 conjunction with 0, or 1 conjunction with 1. And so what that means is that if the number of columns is not the same as the number of rows in the second matrix, then we're not going to be able to carry this out correctly, meaning we're probably going to end up with more entries in the columns or in this row that won't have a pair to take the conjunction with. So these two always have to have the same number of elements. Okay. And that's going to give us the first row, first column. Okay. If now we want to get the first row, second column, then we repeat the process, but now we consider second column. Okay, so 1 conjunction with 0, or 0 conjunction with 1, or 1 conjunction with 0. Alright, and then because there are no more columns, that means that I'm going to end up with just 2 columns in my final result, which makes sense because the ending dimensions of the final outcome is going to be the outer subscripts of the 2 matrices. So we're going to end up with a 3 by 2. Okay, so now we move on to next row. I'm going to move on to second row, first column. In the second row, first column, we'll have a 1 and 1, or 0 and 0, or 0 and 1. Okay, again, I'm taking the 1 and 1, the 0 and 1, the 0 or 0, and then the 0 and 1. Alright, now we go to second row, second column. So still second row, second column now. We'll have a 1 and 0, or 0 and 1, or 0 and 0. Okay. Next one. It's the third row, first column. So we're going to focus on first column again. We have a 0 and 1, or 1 and 0, or 0 and 1. Okay. Now we move on to the next column. third row, second column, 0 and 0, or 1 and 1, or 0 and 0. Okay. So what is the final outcome of that? Well, we're going to have 3 rows, as we mentioned earlier. This one is going to evaluate to a 1, and the rest doesn't really matter what it evaluates to because this is a disjunction. So as long as I have a 1 as part of the disjunction, I'll end up with a 1 in the result. Then here, nothing evaluates to a 1. We have this is 0, this is 0, this is 0. So 0 conjoined, or rather 0 or 0 or 0 will give us a 0. In this case, we'll have a 1 here, so again, it doesn't matter what the rest is, we'll still have at least 1, 1. Then here, we're not going to have any 1s, so we'll have 0. Over here, we'll have a no 1s, so that'll be a 0. And here we'll have 1, 1. So that is the final matrix, Boolean matrix product for these two matrices. And so at the bottom of page 5, we see a claim. We read, let R be the relation from set A to set B, and S be the relation from B to set C. MR is the matrix representation of relation R, and MS is the matrix representation of relation S. Then the composition R of S from the set A to the set C is represented by the matrix MR of S, which is the matrix product, the Boolean matrix. Example number 5 reads, find the matrix representing relations S of R where the matrices representing R and S are given below. Okay, so we want to find the matrix of S of R. That means that we're going to take the matrix of relation R and take the Boolean matrix product with the relation representing, with the matrix representing relation S. Okay, so what that means is that we'll have 1, 0, 1, 1, 1, 0, 0, 0, 0, Boolean product with 0, 1, 0, 0, 0, 1, 1, 0, 1. Okay, so we're going to start by taking first row with first column to come up with the entry in the first row, first column. So that means that we're going to have a 1 or 0, a 1 and 0, or a 0 and 0, or 1 and 1. Then we can move on to the first row, second column now. So that means that we'll have a 1 and 1, or 0 and 0, or 1 and 0. And finally, we have one more column this time. So we'll have the first row, third column. That'll be a 1 and 0, or 0 and 1, or 1 and 1. Okay. Now that we have no more columns, we're going to move on to the second row and start over at the first column. Okay. So that means that we have a 1 and 0, or 1 and 0, or 0, excuse me, and 1. Okay, next we move on to second row, second column. We have a 1 and 1, or 1 and 0, or 0 and 0. Okay. We'll move on to next column, second row, third column. We have 1 and 0, or 1 and 1, or 0 and 1. Okay. Now, since we're done with the columns on the second row, we can continue on to the third row. So third row, first column, we'll have 0 and 0, or 0 and 0, or 0 and 1. Then next column, we have 0 and 1, or 0 and 0, or 0 and 0. And last column, we'll have a 0 and 0, or 0 and 1, or 0 and 1. Okay, so now that we have all those listed, we can go ahead and evaluate. None of these, well actually one of these is going to evaluate to a 1, so we'll have a 1 here. Then here we'll evaluate the first conjunction to 1, and then in the third column we have the last conjunction evaluate to 1. Then for the second row, we don't have anything evaluating to a 1, so that'll be a 0. In the second row, second column, we'll have this evaluating to a 1. And the second row, third column, we have this conjunction evaluating to a 1. Third row, first column, they're all zeros. Third row, second column, again, all zeros. And then third row, third column, all zeros again. So what does this mean? Well, let's go back to the original matrices. That means that R contains the elements, let's see, A to A to C, B to A, B to B. And S contains the elements, again, if we assume this is A, B, and C, A to B, B to C, C to A, and C to C. Okay, so if we take S of R, that means that A maps to A and then A maps to B. So we should see A comma B as part of our our composite. So that means that we would have a 1 at this position, which we do. So I'm not going to list all of them out, but I do encourage you to maybe go through that process of taking the mappings of R and the mappings of S and seeing that you actually get these elements as part of the composite. So I'll get you started with it and then you can verify the rest. A maps to A under R, it also maps to C. B maps to A, B maps to B, and those are the 4 elements that we have as part of B. As part of R, as part of S, we have A mapping to B, we have B mapping to C, we have C mapping to A, and C mapping to C. So now based on that, we have A maps to A and then A maps to B, so we should have A to B, which is here, right? This is A, B, C, A, B, C. Then we have A mapping to C and C maps to A, so we should have an A to A, which is here. C also maps to C, so we should have an A to C, which is here. Okay, then for B, it maps to A, and A maps to B, so we should see a B comma B, which is here. B also maps to B, and B maps to C, so we should see a B to C, so that's here. And then finally, C doesn't map to anything, so we don't under R, so we never get C mapping to any of the other elements under the composite. And that's why we see all zeros at the last row.